going live. Hello, everyone. Thank you for attending our Dev Days European Conference 2022. I hope you enjoy yourself and all the topics are very interesting for you so far. We have prepared a lot of more interesting talks for today and tomorrow, so stay with us. I just want to mention that at the end of the session, we will have time for Q&A, and you can write your questions at the Q&A section whenever you have one. You can freely write it during the session as well. And at the end, we are going to have our speaker to answer them. Keep in mind also that our knowledge partner Pact will be giving away 20 ebooks to most active conference attendees. So we kindly urge you to participate and be active, rate sessions, leave comments, ask questions, and you can win, of course, a great ebook from our partner Pact. Now, let me introduce you our speaker, Chris Condron. Chris is a software engineer and architect who's been building message-driven and event-sourced systems for over 20 years, and is currently working at Event Store. He has a vast background working in the telecom, finance, and biomedical industries, delivering, supporting, and transforming mission-critical systems in environments ranging from the Fortune 500 to companies just starting as startups. The name of the topic for today is data modeling in an event-centric world. And in it, with practical examples, he will walk you from traditional relation and data models into the best practices event models. In addition, he will apply well-known rules from traditional modeling to know why these new models are ideal for various usages. Now, Chris, I'm giving the stage to you. It's you.
Hello, everyone. Good morning or good afternoon, as appropriate. Let me share my presentation here. So I've been doing this for quite some time now, and what I want to talk about is how do we really bring those tools that we've got from relational systems into all these event-driven, worlds where often our modeling is very weak. So I'm going to start off a little bit with some primer material that I'm going to go through fairly quickly, but there's a lot of misinformation out there, and so I find starting from a foundation of really good background about why we're doing things, what we're doing, defining and organizing some core concepts really sets us up to fully understand how to do the transformation and modeling between data-centric applications, and I'm going to be comparing it to traditional relational applications. So for me, the goal here is we want simple, scalable, cloud-friendly applications. And the reason we're going with events really boils down to simplicity of distributed systems. If we could make everything work locally against a relational database, that would probably still be the way to go. That's why it was so dominant for so long. But as we move into the cloud and other places, we've got to look at these other things. And really in the cloud, the combinatorial complexity of what we're doing becomes really problematic and important. We have one element, it's easy. We have two, it's easy. When we have three, all of a sudden now our complexity goes up to 6. Just one more feature. And now we've got to do retries and message problems and patterns like that. So it's very easy to see how simple additions can make a huge problem. So in the real world, that's where we get schemas like this. And this is a real application that is a flagship application, makes people a lot of money. If we look at it, drill in, that central table is managing all of the insurance policies or accounts or whatever. So we can see that this gets to be a real problem in production. And even going with microservices doesn't solve it if we just recreate the problem at a higher level. So what we're trying to do with event-driven systems, and I I was asked if I could have one law, if one thing I was remembered for, this would be it, right? For me, anytime you get more than 5 degrees, 5 systems with degrees of freedom, you can't understand it. You can't fix it. You can't do anything. So, what do we want to do? We want to reduce the freedom. Simple way to do that, traditional layered architectures, right? All of a sudden, this is why that pattern is popular. But what we can do once we start looking at CQRS event driven systems, we realize that if we look at the top of this, it's our UI coming down through a business logic, persisting, and then coming up through read models, we can create one way pipes with the same number of components. These pipelines we can then scale. We can put our dynamic loading in. We can do all the things that we want to do in the cloud. And the way we get these all to work is with these events. So, anything with more than 5 degrees of freedom, you can't understand what you're doing. You can make it intelligible by making pipelines of events. Once we have these events, now we need to go and store them. So let's look at our core types of storage that we want to be looking at. Relational, we all know it. This is going to be our comparison, sort of the first real thing that became serious about data storage. Graph databases, right? Different fundamental model allows you to do queries that are not possible in relational. If anyone's ever folded organizational hierarchy into a relational database, it's awful. A graph database works really well. Document databases. We started off with state bags and web apps. Now we have MongoDB and other really excellent document storage databases that allow us to get to different pieces, not really caring about the schema or coupling the way we do in relational systems. The last one is one that's actually been around since before relational, but was never really called out: ordered storage. This is where you write everything down in order as it occurs, right? Persist everything as data, appending in the order it receives in an immutable log. We use this all the time. Your event logs from your application, logging out. It's exactly how it works, right? It's a very well-known pattern. The ledger. The ledger has been around since the 1600s. This is what blockchain is built on top of. It's a simple ledger with distributed with proofs on each record that's entered. Event streams are used in things like the stock market. So again, an ordered series of things which have happened, right? Now, once we have those things and we're looking inside this ordered storage, how do we actually implement applications in this? So we understand the goal, we understand the type of storage we're using, ordered. Now we're looking at the patterns. So fundamentally, and this is where one of the things that gets a little confusing is people conflate event sourcing, which is what we're going to model, with these other types of ordered storage. So commands are requests. Please add this box to the warehouse. State snapshots, inventory equals 80. That is just a frozen point in time. Doesn't give you any history on what's going on. Change data capture, inventory was incremented by 1, throws away all your context, but it's still part of that state snapshot. Events are decoupled because they're saying this thing happened to the warehouse. They stand on their own, right? So event sourcing, which is what we're going to model, is keeping application decisions persist as an immutable sequence of business events. Not changing the capture, not state snapshots. This is all about business events. This, I normally ask if anyone recognizes what this is. This is a physical representation of a Turing machine. And that's what we're going to use. So now that we have our stream of events, every one of our microservices or processors turns into a simple Turing machine, right? So this is our Turing machine, and this is our log along the bottom. If we're saving the input, we're command sourcing. If we're saving the internal state, either the snapshot or changing to capture, that's state logging. It's when we save the output of our state machine, of our microservice, the event, in that ordered log, that's event sourcing. This is what we're going to be modeling, not the other two applications, right? And what's important here is that series of events that we are modeling, and this gets back to proper modeling in like a third domain, third normal form or entity modeling. The schema should be independent of whatever microservices are running. The event should be a business activity with a schema that we can really store and understand. If I see that, we added a box, we added a box, we added a box, we put 2 boxes on a truck, the business should understand with a schema separate from the warehouse manager or the truck manager tracking service, right? So this is the model we're going to be looking at. Now we're going to be modeling this up. We've been talking about a raw log, but a raw log isn't really a database. What we're really going to need to look at is like a stream database where we divide these streams up into fine-grained components. The same way if we had a relational database with, say, 4 tables and everything was in 4 tables, that's not really a relational data model, right? We need something more fine-grained to control what's going on. So while we have the core event log that we see down here in order, logically inside of that we have individual streams. And you can see that each stream has an auto-incrementing ID on every event and has a position in the global log. Furthermore, we can do projections or effectively what we would call a table view inside SQL Server that is a new ordering of some set of the event log. So an event source application is you have multiple microservices being writers. Each one is generally going to be targeting a single stream for writes. So its state will all be managed on that single stream. But then the readers or the processors will be going across the entire set of data available inside the system. And what this allows us to do is keep our microservices isolated the way we want to, and allow the application as a whole to still remain context on what's going on. So this allows us, because of the structured independent silos of data, to have more than one microservice in the same, backed by the same database. Whereas in other database approaches, generally that's not a good idea because you wind up with more coupling than you want. But this isolation allows you to have them each with a dedicated stream for writing and reading their state. But now, when I go to run a report or track a process across 3 or 4 different microservices, I have a shared context I can do that with. And everything on the data modeling side, everything on the analytics side becomes far, far easier. These are the attributes that you want to be looking for as you do this. You want fine-grained streams, sequential numbering, global ordering, optimistic concurrency for locking, because we have pools of workers. We want those workers to say, hey, I know where I'm at. I'm trying to put the next thing on. That's outside of the scope of what we're doing here a little bit. You want something that's a database. You want to be able to do positional queries, push notifications, and catch-ups. And by fine-grained streams, the best way I can say it from a data modeling point of view is you want a stream per row not a stream per table, right? And we'll see that as I get into the modeling a little bit later. So we have our stream database. What we're going to do is we're going to add in projections to that hierarchy of what we call categories. And these are going to act as our tables, if you will, for the data. So I've got an individual stream. I've got foo and bars, two topics here. I have a stream per instance. So every single instance, even if there's millions of them, of foo, have one stream that logically tracks its position. And then the category is at the table, if you will, that's going to wrap those individual instances. And that gives me ordering on the global level, ordering on the table or my category, and then ordering on my individual instance or row. Now, we're not going to be doing quite the same way we're doing, but we get into that in a second. So now let's go back to how tables and tuples and what we look at when COD first came up with a relational model. So when I'm talking about a relation here, I'm using that original definition where the relation is the row of a set of related data. And in the relational database, what they do is they group relations with identical schemas into tables. And then on top of that, they've allowed all sorts of joining in primary keys and foreign keys and other things. But that's the first concept, is that a relation is a row. Tables are sets of relations with identical schemas. And we're going to be looking at an invoice application here. So when I do modeling in my relational database, I'm going to take and I'm going to do my third normal form, which says, hey, we're not going to repeat any data, right? We're going to be nice and tight. This is a right side model. And I'm going to use foreign keys from my tables to other tables to break everything out. So what we see here is we have customers. And in this model, it's very simple. I have a single tuple for customer, right? And that has an ID, the name of the customer, the type of customer, and payment terms. Invoices has three tables that we've used to model this. So we have the primary table with the invoice ID, foreign key to customers, the date of the invoice, and a top level description. I've then in this model chosen to have the line items as a separate table. The line items have individual IDs, but then they reference the invoice ID. And we can see the invoice 1 has 3 line items, and invoice 2 has 1. And again, we have a different schema or different relation here, different tuple. And then we have a payment status, which is a third table. What we're going to do now is we're going to look at what categories this would map to in our event model, right? And what we're going to say here is that because it is per instance, right, we're going to say, okay, the customers are one category and the invoices are another. Because all three of these tables, if we look at the IDs, right, this invoice table has a primary key, and then each of these are really all references into that first table. So we can see how all of these invoices really model one logical business concept. And then over the customer side, in this model, obviously, we have a very simplistic customer model with an ID and a single tuple, right? What we're going to do is now we're going to say, okay, we've got categories of customer and categories of invoice. And in this model, we have 2 customers and we have 2 invoices. And we can see that if we go back up here, invoice 1, invoice 2, customer 1, and customer 2. The twist we're going to make is that rather than organizing all of the tuples by schema, we organize all of the tuples by the business ID. And in particular, what we're going to be saying is that the tuple or relation inside a relational database becomes the event. So each event is effectively equivalent to this tuple. So my create customer event is going to have, you know, the type of operation and then all of the data that's in this schema. So if we look here, we give it a name. So we take our insert, update, delete, and we give that operation a name. So now it's add customer, which would have been our insert. And then we then go through and we have, you see here, right, the stream becomes the ID, customer -1, that's our ID. And then the three data elements are what we're doing here. And then so we can see that we added customer 1 and we added customer 2, and the data is there. The difference with this model is that now I can have an update, which I'm naming term extension negotiated, which has on it net 90. So this data model keeps with it all of the power of the relational model in the third normal form, but it adds in the detail that we can now see that the payment terms changed. I now know the history of what happened to this customer. So I can see that Bob's Tires started out net 30 and then we extended them to net 90. And that information isn't lost. So what we're seeing is that the model with event data is actually richer than the model with just the relational data, right? If we're doing the proper modeling, we understand the schemas. Now let's take a little at a more complicated example, our invoice. Over here on the right, again, we have two invoices. And what we're seeing here is, again, we've named our insert add invoice. We have the customer ID, we have the date, and we have the description. If we go up here, we see that's the exact same data. So again, the primary key becomes the stream identifier, right? The category invoices is, so we have category dash identifier, it's our naming convention, that gives us our ID. Then we have the data. What we're doing here is we're using, the other one thing I want to talk about here is this reference to the client ID. When you're writing events into a primary store as your source of truth, each of these microservices, writing the events. If you remember before, we had, let me go all the way back up here. We're writing to a single column. These writes want to be in a third normal form. We want them to be fine-grained, non-duplicative, just the changes. The consumers, the readers, the processors are going to be producing first normal form style data. We want to bring all these streams together to produce the data our applications will consume. So the entirety of this model for storage is write optimized, and then the consumers, which have really great benefits with cache invalidation and optimization, produce our first normal form for consumption. So let's go back to walking through our invoice. So we add an invoice, and then you see we add a line item. Another difference here, line item is a tuple, which in a relational model would be in a different table. But in an event model, because it is about that invoice, it's a change on that business object, they all go into the same stream, right? So now I have events from add invoice, add line item, add line item, add line item, payment received, right? And we can see that very clearly modeled up here. 1, 2, 3, 4, 5 events, 5 tuples, 5 rows. The invoice 2, we're all going to take a look at the same thing, but again, we're going to see this retention of history, right? We add the invoice, we add the line item, We added a second line item, and then we removed line item 5, right? And so all we needed to do here was reference the key on the first one, because again, we're going for that third normal form, don't duplicate data, right? So this is mapping the events that we're seeing inside our structure of the core log with the overarching order. The categories, generally each microservice will have a category, or each business object will have a category, depending on what you're modeling. And then there'll be instances inside that. And then if we're doing a microservice pool, then we'll farm out work to different workers in a dynamically scaling pool of microservices per instance to make updates to those streams. So that covers how we're doing the core modeling there. Now let's talk about different ways. This is one way to do a default read model or default first form style of data on the same categories that we've been doing. In practice, you should build the read models based upon what your target needs. But let's talk here about how do we model this. If we take a look at a sparse columnar store, that's very similar to what I refer to as the default read model for a category, what that would be. Here we've got different events, and what we're assuming is that even though up here we said that we're going to put events from different what would be tables in here, because we're doing a third normal form style right, I'm assuming that none of these columns will have duplicate data. Like the invoice ID here, the invoice ID here, and the invoice ID here in all three places is the same logical data value. So that's why we're saying A, B, C, D. So the union of the data elements on all of the events that are defined inside a category forms the default read model for that category, right? And so we can now map each event as a change on all of those elements. And we can provide a default read model that has the current value for all of those. And in practice, because we're doing this, it doesn't necessarily need to just replace. We might have a custom read model where we sum them or do other operations on what we want there. But the default one is, what is the last value for each one of my elements in my union, as if this was a column or store. So I guess if people have questions, they can put them in the Q&A section. That's my quick summary. Normally I like to do this with a live audience when we're all going to be able to be back in person and do a little bit more interactive and drill down on questions people might have. Please feel free to type any of your questions into the Q&A section on this. So now the other thing that becomes really important as we're actually building systems with this is how do we get these read models out to our consuming applications, right? That's one of the reasons why we're doing atomic increment on the prefix in the column. And what we mean by that is if we go back up here to our stream, we see that we're not doing a monotonic increment. Most logs will implement their core event log with a byte offset from the start of the log. And that gives you a guarantee that any log position you see is equal to or higher than, and you can do a lot of comparisons on that, and it's great. But what it doesn't give you is a concrete notification of whether or not you've seen everything in a stream. And this has tremendous implications for cache invalidation, and this has tremendous implications on the simplicity of getting this data out. Because we're doing append only, and we've added into that fine grained streams, and we've added in this atomic increment, which is exactly the same as an auto incrementing ID in a table in a relational database, only we've turned it and added it to the row. That means I know as a consumer for stream one, this fine grained element, I should always see events in order and without gaps. Monotonic or the byte offset won't give this to us, but an atomic increment will let me know if I see 1, 2, 5, I know I've missed messages. I either I've missed them or they're out of order. I can implement a very simple solution to say, if I'm consuming on a queue and I see a gap in what I'm expecting to update in my read model, I can go back through a backup channel and query for those missing events. And then when I suppose I miss events 3 and 4, I see event 5, I go, okay, wait, I'm missing 3 and 4. I query for 3 and 4, apply them, and then I apply 5. If they were simply out of order, if I just had some jitter, I then just drop 3 and drop 4, because the only way to make a change is to have event 6. So I can be very deterministic in what I'm doing as I move forward. And this greatly simplifies my data caching and my distribution. Further, my data caches can now validate with each other that they are in sync without needing to go back to the core server. I don't need to read a central server to know whether or not I'm cache aligned with something else. This means if I've got a database producing results from warehouses in Chicago, and I have 2 business users reading reports in New York and LA, I don't need to go back to the database to find out if those reports are in sync. Furthermore, unlike eventual consistency, this ordered consistency or this quantum consistency allows me to know that I'm never wrong. I might be stale because we can't get around that, but there's always going to be a level of staleness, and I can manage that through an active service that's comparing the core position on the server to the core position on my distributed report. So that's what the quantum consistency, and we're using quantum there in terms of quanta, so the event becomes the minimum unit of change, right? And that's our quantum, and all of the events are atomically ordered for their context. We're also linearizing everything. So we get, if you go to the Jepsen page, we get linearized, serializable updates. And that's what allows us to completely simplify our cache invalidation. And now everything becomes fully deterministic. We're not guessing, we're not trying to figure this around. I don't need to run a consensus protocol. I just need to check a single value. Everything becomes a vector clock, right? And that tremendously simplifies everything. So let's talk about how that quantum consistency, we're doing consistency based on a set of ordered and atomically incremented events works. So we have our database, and we've got, normally we write our data going forward, but we think about what our consumers are going to see. This is a propagation queue of events. Consumers should see events in reverse order. They're going to see them increment up 1, 2, 3, 4. So this is the propagation of events out from a central store, right? So reporting and analytics can be at position 2. We have an external integration that's at position 3. Our memory cache and our UI display are at 6, right? So if my UI display wants to send a user command to a service, that service is going to know that the log, so we have a service, that service is running, the service is up to date at number 10. The user is only seeing number 6. They're going to send a command, but because the service knows everything from 7, 8, and 9. It knows enough to apply the command and update the database at position 10. Therefore, this is our optimistic concurrency. Therefore, we know it's safe to make this change because nothing else has happened. But if we have a process manager without any user interaction that sees something in event 8 that it wants to update the store, and all of these are interchangeable in terms of what they're doing, the store has already moved past 8. So that process manager is going to get a failure on write, and it needs to go back and read 9 and 10, which it can do with a direct query, and then it's going to be able to update the store. So this is how we can allow pools of independent workers to be operating on a moving stream, and only when we're trying to update the store do we need to do an optimistic concurrency check, which is the most efficient. And we're doing it on these fine-grained streams. We're not locking the entire invoice table with 10,000 invoices and 500,000 events. We're locking this invoice. And we really want that lock. We want to know that, okay, you can't change the quantity on a line item if the line item has been deleted. Those are the kind of locks that we want. So that's how this all works. And we get that multi-level atomic ordering from good ordered storage systems or stream databases. And we can do that at the log level, at the category level, or at the stream level, depending on how much we need to lock. We want to lock as little as possible and not join things, but we want to guarantee that consistency. In a larger system, this system that I've been talking about is going to be playing inside of generally a larger ecosystem. So the hexagons here are, a call out to Alistair's hexagonal architecture. We're going to say that each domain or each component is going to have this type of fine-grained event source internally for its updates and its OLTP, right? So we're going to do that third normal form writes, first normal form reads. When we bring multiple applications together, what we want to do is use an anti-corruption layer to transform our internal events to public first normal form events to go on a distributed bus for consumption in unknown other apps. This is going to be your Kafka, Kinesis, Azure Service Bus. We don't want to share this private data any more than we would have wanted to share a private schema in a relational database with another application in that database. We want to use a public schema with first normal form sensibilities. We don't want downstream consumers in this model, where they're not part of our app, to be doing these callbacks on a regular basis to us. So we want the full set of data. We want repeat fields. So everything that's happened is available in order to, for the consumer. We sort of want to wrap it up so the consumers get the full picture. Some examples of this might be when I've written trading systems, I can have a placement might be like reserve the amount, send it out, and do 3 or 4 back and forth internal events. But then once the order is placed, I have a single public event, which is published to all other systems saying this order has been placed. They don't need to know my internal checks with 3 or 4 different microservices to confirm the placement. They only care this has happened. Here's all the information about that order. Again, private APIs, public APIs, third normal form, first normal form. It's all the same thing. We're just taking it and distributing it in a wider area. Copying from Strunk and White here, keep it sparse, keep it sparse. Your internal events should be tight, third normal form, don't repeat data. You should never put data on an event for the UI. That should be the job of your readers, to pull that data together. Flag fields and nullable fields generally mean you haven't modeled your data correctly. Break it down into finer events. Model your process history. How did we get here? Not where are we at. You can always calculate where we're at from how we got here, not vice versa. The application is what's going to enforce these circuit keys. With event-driven systems, it's outside the scope of this. You can really enforce the testability you need to do that. And again, I already talked about no display data. So, questions? Either in the chat or in Q&A. All right, I don't have any questions. I do have, are you seeing any questions there? I'm not hearing you. How obvious is the mapping?
It was very informative. I think we don't have any questions. Hear me now?
So I do see a question. How obvious is the mapping? Yep. How obvious is the mapping from tables to categories? Generally, all you need to do is track your primary keys. What you're going to find is that the payment table is always in reference and always has the primary key of the invoice table. If a payment can stand on its own, or if a payment was to a customer, then I might map that differently. But generally, it's the same level of mapping that we do if we're doing a third normal form modeling. So you trace your primary keys, it becomes very obvious. How big of a solution would you need to justify going event-based? I find that the real question there isn't the size of the project, it's the transition of the team. The team needs to learn how to do event sourcing. Once your team understands how to do it, I generally event source everything. It's not about project size. So if the project is important enough to your company and the data you want to save is important enough, or you're moving into a truly distributed world, then it's generally worth it to train your team on how to do this. If your team knows how to do event driven, then event sourcing is a small leap. If your team only knows relational, then it's a bit larger. So it's really about the team's familiarity. And once you start looking at things like this modeling, it actually lowers the bar to doing that transition quite a bit. And I would say if you're in the cloud, if you're distributed, it's worth it, 100%. Yes, aggregate roots in a domain map one-to-one to categories. I use categories because it's more generic, and I don't want to enforce that you have to use domain-driven design. Given that, domain-driven design is one of the best ways to find your events and find your categories. Follow language is a great technique. It's not required. But yeah,
thank you, Chris,
almost always. Okay?
Yeah, okay.
Yes. All right, thank you again, everyone. We're at the end of our time, and thank you again for the questions. I hope this was informative.
Thank you, Chris. There are no more questions. So if you are ready.
Thank you very much.
They were very informative, the answers. For attending that session. very interesting. Just to let you know, the last one today. There are no more sessions in the data path. We will be waiting for you tomorrow with